Hello and welcome everybody to this talk. The aim of today's presentation is to give you an overview over the polarization capabilities that are built into Quadoa Optical CAD. Before we start, a short overview over the outline. So I will begin with the state of the art and the challenges of how polarization is typically implemented into optical software. Then I will show how we have implemented the extended Jones and Müller calculus. I will present some analysis features that can be used in combination with these polarization features. Then we will go onto birefringent materials as well as birefringent coatings with birefringent coating stacks, and finally some examples and a conclusion. As you probably already know, there are two main methods that are typically used to simulate polarization, one being the Jones calculus and the other being the Stokes-Müller calculus. The Jones calculus can be used to simulate fully polarized light, and you also can obtain the phase information for each of the electrical field planes, whereas the Stokes calculus can also be used in addition to simulate partially polarized light. However, it does not contain the phase information. Now, in order to simulate, let's say, a linear polarizer or a wave plate, we can define a Jones matrix that does this operation. And since the linear polarizer or wave plate is an element property, we need to define the matrix inside the local surface coordinate system. The problem now arises if we have rays that are tilted in respect to the surface coordinate system. In this case, we somehow need to transform the electrical field of the ray, which is in the 3D space, into the local coordinate system. So basically the problem is like how to apply the 2D math of the Jones vector or the Stokes calculus to the 3D electrical field. To see why this matters, let's first take a look at this interferometric setup. In this case, we have a collimated laser beam here, and it hits the polarization element perpendicularly, and therefore in this case it's totally valid to simulate a wave plate or a polarizer with a simple Jones matrix or a Müller matrix. Now let's look at a second example. This is a pancake lens, as it can be found, for example, in the area of virtual reality goggles. And the idea here is that we have this sequence where the light reflects from this and this surface, and this is the sequence that we want to use, but we need to somehow avoid the direct transmission of the light as it would normally go through a lens. And this is achieved by adding polarization elements to the optical surfaces here, and these need to somehow be modeled in the optical design software. The difficulty in modeling this arises from the fact that the rays are tilted in respect to the surface coordinate systems, and therefore we cannot directly apply the Jones matrix to the rays, but we need to somehow convert the ray to the surface coordinate system. Unfortunately, there isn't a single ideal method on how to apply this coordinate transformation. Therefore, in Quadoa, you can choose between different options. The first option being the projection. In this case, the 3D Jones vector is projected, like the shadow is projected onto the surface. And the advantage of this method is that after the linear polarizer, for example, you get linear polarized light independent of the orientation of the polarizer. However, the drawback is, since the C component is ignored, energy is not conserved in this case, which might be bad in the area of illumination. The second method for the coordinate system transformation that is available in Quadoa is visualized in this picture. It works by rotating the ray until it's perpendicular to the surface plane. And the advantage of this method is that since we do not ignore the z component of the vector, the energy is conserved. However, if you look at, for example, in this case, we have these circular polarized rays, and they hit the surface under an angle, and then we get linear polarized light out of the linear polarizer. However, the polarization is rotated depending on the position of the pupil. The third option is similar to the second option. However, in this case, the ray is not bent along the sagittal plane, but along the x or the y axis. And this has the advantage that if we have, for example, linear polarized light in the y direction and we bend it along the y direction, we get a linear polarization in this case. However, again, if we have linear polarized in the other direction, we will get this curved polarization state again. So it's better in one axis, but with the drawback of being worse in the other axis. And also in this case, the polarization energy is conserved. To draw our first conclusion here, we can see that with all these methods, there's always some trade-off between the energy conservation and a more or less correct polarization state. And which method is best for the task we want to perform depends on what kind of polarization matrix or Jones matrix is to be applied, but also on the analysis that should be performed. For example, if you want to analyze the polarization or the intensity. And this is especially a problem since the polarization is often relevant for coatings, ghost analysis, and all these things where both like intensity and the polarization state is important. And in summary, the problem is that we do not have a general solution for all these tasks. Another limiting factor for the Jones or the Stokes calculus is that an element typically cannot be defined by a single matrix. For example, if we look at this wave plate, then the optical thickness of a ray depends on its angle, and therefore also the retardance is dependent on the angle, which means that we need a different Jones matrix for each angle to pass through the surface. Another thing is, for example, if we have dispersion in the birefringent material, in this case we will get a different retardance depending on the wavelength of the light. Or also, for example, if we have the retardance is different over the pupil, which is, for example, the case for stress-induced birefringents, then we also need some kind of modulation to the Jones matrix over the pupil. Now let's have a look at how the Jones and Müller calculus is implemented in Quadoa. First, the software provides a wide range of predefined Jones and Müller matrix elements like general Jones matrices or linear polarizers, wave plates, and for the cases where for example, the retardance depends on the wavelength or the incident angle, also these interpolated items are available. Quadoa fully supports the Jones as well the Stokes-Müller calculus for partially polarized light, and the methods for how to get your 3D electrical field into the local coordinate system can freely be chosen for each element. The items are compatible with any of the available surface geometries, which means that you can also add, for example, a retarder to a curved surface or a A-sphere and things like that. And also more than one polarizers can be defined for a surface, for example, if there are two sequences, one for reflection and one for transmission. And all the, I already mentioned that, all the pupil position, incident angle, and wavelength dependent polarizers can be defined as the interpolation tables. Let's have a quick look at Quadoa itself. We can see that in the sequence source settings, we can define the polarization state, for example, like a linear or a Stokes polarization. In the 3D view, we can also show the polarization state of the rays. For example, we can see the polarization changing when we rotate the faceplate, and different polarization items can be added via the coating tab or also via the right-click menu. Now let's have a look at the analysis features that are available in Quadoa. First, as I just showed you, there's the 3D view in which we directly can plot the polarization ellipses, and this is especially useful if you have complex folded systems and you want to track the polarization state throughout the system. Then there is the polarization map that can be used to plot the polarization ellipses over the pupil. The ray tracing report shows all the ray properties like the direction of the ray, the position of the ray, optical path lengths and all these things, but it also can be used to plot any polarization data. And for example, the electrical fields can be shown, the orientation or the ellipticity of the polarization ellipse, and in the case of partially polarized light, also the Stokes vector as well as the degree of the polarization can be shown. Besides this, there is the Poincaré sphere plot, and for example here we can see all the rays and all of them are linear polarized and a part of them is only partially polarized. In addition to this, all the analysis features, for example, this is the point spread function, but also the MTF and also the wave optics functions, all rely on the polarization ray tracing, and this means that, for example, if we have a unpolarized light and then we have the same system but with linear polarized light, we can see that there's a difference in the point spread function. Another analysis feature that relies on the polarization ray tracing is the irradiance plot, or in this example the ghost irradiance plot. And in this system here, for example, we have unpolarized light that is entering the system and it is defined via a Stokes source. And since the Fresnel reflections may partially polarize the light, it gets linearly partially polarized throughout the system, and this, for example, may also affect the outcome of a ghost analysis. So in the case of unpolarized light, it's always recommended to rely on Stokes calculus instead of Jones calculus. Up till now, all the features that were presented were based on the classical Jones or Stokes calculus. So let's now move on to a more physical approach based on birefringent materials and coatings. Jones and Stokes calculus can be a useful tool for many problems. However, as shown in the beginning, there is no general solution for the transformation from the ray into the surface coordinate system that's valid for all cases. And also for some cases it's required to assign some kind of interpolation tables to these Jones matrices. So the question is there maybe a better solution to this problem? And here the idea is that we do not rely on a single Jones or Müller matrix element to define our optical element, but instead really physically model the anisotropic materials and also the coatings. To achieve this, the first thing that is required is the definition of birefringent materials, and for this Quadoa offers a wide range of different dispersion formulas that can be used to define those materials, and for each material always the extraordinary and the ordinary material can be defined. This can be done as Sellmeier equations, other, for example, Schott equations, or also interpolation data with the refractive index and the extinction coefficients. Inside the optical design editor, then the material can be referred as any other material. However, in contrast to normal materials, the additional parameters that define the crystal axis will appear in the material item. And the important thing to know here is that the crystal axis is always defined inside the element coordinate system. And this is really important, for example, when it comes to tolerancing and a surface tilt is, for example, applied to the first surface, then this will not affect the crystal axis, which would be the case with a classical surface list-based optical model. To obtain both the ordinary and the extraordinary beam path, we can utilize Quadoa's multi-sequential ray tracing, and for this we set up two sequences, and for all the surfaces that enter a birefringent material, there's the option to choose in between the ordinary and the extraordinary path, and by selecting this we can generate these two sequences. Besides element materials or lens materials, the birefringent materials can also be assigned inside a coating stack to the coating layers. And this means that you cannot only define isotropic coatings, for example like RR coatings, but also birefringent coatings, for example for thin film polarizers. Coating layers can be defined in different ways, and there are also operators, for example loop operators, to automate coating definition. And the calculation that we have implemented to compute these coatings are the classical transfer matrix methods for the isotropic coatings, and the birefringent coatings are based on this publication. In summary, this means that there are two options to define a birefringent element. One is as a birefringent volumetric element. The other option is as a birefringent coating. The advantage of the coating is that we directly get the combined polarization state out of it. However, the beam displacement is ignored in this case, whereas the birefringent element, for this we need to trace both sequences, one for the ordinary and the extraordinary ray. This means we also get the two polarization states as well as the beam displacement. However, if we want to get the overall polarization of the recombined fields, then we need to recombine those in a detector plane. Now, to see what we can do with all these features, let's take a look at some examples. The first example is a birefringent crystal. It's illuminated by a beam, and we are using the wave optics toolbox to analyze the outcoming beam properties. We can see that if we look at the individual sequences, then we get the vertical as well as the horizontal polarized beam out of the crystal. And what we can do now is we can overlap the two polarization states, and we get the combined elliptical polarization state. And we can also use the wave optical interferogram analysis to overlap both the beams, so we also get the overlapping intensity and phase. The second example is a quarter wave plate that is hit by a diverging beam where the rays are circularly polarized. If we model this with a simple Jones matrix, then we can see that we get out perfectly linear polarized light and we get a uniform illumination. Depending on the projection method, we can also obtain different results. Now, if we have a zero order wave plate, we can model it as a single uniform layer of a birefringent material, and we can see for this ideal or zero order wave plate, we get some kind of ellipticity at the edge of our aperture. And also if we plot the transmission over the angle, we can see that there is a fall off at an angle above around 45 degrees. The same simulation with a different wave plate, in this case it's a multi-order wave plate, again modeled with a single uniform layer but of a higher thickness. And in this case, we can see that the light is linearly polarized near the optical axis. However, to the outer regions, we get some circular polarized light as well. And also, if we look at the transmission over the angular spectrum, we can see these ripples occurring. The third example is a linear polarizer. Again, we are illuminating it with a diverging beam that is circularly polarized, and the ideal Jones matrix polarizer results in a perfect linear polarization, and also the horizontal light is completely transmitted, where the vertical polarization is completely absorbed. Now, in addition to this, we have modeled two polarizers. The first one is a absorbing polarizer, where the extinction coefficient is really high in one direction, whereas it's low in the other direction. And if we use this kind of polarizer, then we can see that at the edge we get, first we get also linear polarized light with a slight ellipticity at the edge. And we also get the fall of the intensity to the side, which we can also see here in the plot of the intensity over the pupil. The third polarizer is a thin film polarizer, and this one works by utilizing the Fresnel losses at the interface between a isotropic and a anisotropic material, which leads to the reflection of the one polarization state and the transmission of the other polarization state. And for this kind of polarizer, we can see that, again, we get linear polarized light in the center. However, we get different polarization states in the outer regions. And the advantage of this polarizer is that the fall off is pretty low up to a certain point, but then we get this breakdown of the intensity for larger angles. Just another comparison in between the two polarizers, the absorbing polarizer and the thin film polarizer. Here we have a system where we have two crossed polarizers, and you can see that it strongly depends on what type of polarizer you are using, and you get really different results, and all of this cannot be covered by a simple Jones matrix. So you really need to model these polarizers to see what's really happening in your system. The next system is a thin film coating, where the thickness of the birefringent material is defined by a Zernike polynomial, and this leads to a pupil-dependent birefringent. Behind this coating surface, there is an additional surface with a linear polarizer, and if we run an image simulation of rays running through this surface, we get this colorful image, which is, for example, similar to what you would get from things like stress birefringents. Finally, a last example. In this model, we have an interferometer with the blue sequence being the test arm and the red sequence being the reference arm. And if we just look at the optical path difference, we can see that we get these fringes because of the tilt of one of the mirror surfaces. And also, if we use the wave optical analysis, we can see that the fringes, we get the same result as with the just looking at the optical path difference. Now, however, if we introduce some birefringence here, which is done by this additional surface here, then we can see that the interference shifts. So first there's a phase shift occurring through this birefringence. And then also here in this area, for example, the contrast is smeared out just because the polarization states do not align anymore, so we do not get any interference in this area. Now I'm already at the end of this talk, and I will finish it with a short conclusion. I've demonstrated that the Jones as well as the Müller matrices should only be applied to collimated beams, and in the other cases it's important to really be careful with the method that is used for the conversation of the coordinate systems. Then for the incoherent light, Stokes calculus is to be preferred because light might get partially polarized during the path through a system because of Fresnel interactions. Also for birefringents, depending on the system to be modeled, typically it's useful to use multi-sequential ray tracing so we can really see the different paths of the ordinary and extraordinary sequences throughout the system. And finally, to really accurately model polarization optics like birefringent coatings or beam splitters, typically physically modeling is to be preferred. Thank you, and I hope to see you again next time.